Imagine standing just a few hundred feet away from a 30-story building. The concrete towers above you like a mountain, steel beams disappear into the clouds, and thousands of tons of material seem impossible to move. Then a machine extends its arm nearly 70 meters into the air and begins tearing the structure apart floor by floor. What you're watching isn't science fiction. It's one of the most powerful demolition excavators ever built. Most people see demolition as destruction. But here's what nobody tells you. Every controlled collapse requires astonishing precision. A single wrong movement can send thousands of tons of concrete and steel in the wrong direction. The operators controlling these giants often spend years mastering skills measured in mere centimeters. Think about this. Some demolition excavators weigh more than 200 tons. Their hydraulic systems generate forces powerful enough to crush reinforced concrete that once supported entire office towers. Yet those same machines can remove a single steel beam with incredible accuracy. Power and precision rarely exist together at this scale. Today we're following the incredible journey of these mechanical giants. From iron ore buried deep underground to towering machines that reshape city skylines, you'll see the mines, foundries, factories, and testing grounds that bring them to life. And what happens before the first piece of steel even reaches the factory might surprise you. Every demolition excavator begins its life deep beneath the Earth's surface. The primary ingredient is iron ore, extracted from massive mines in Australia, Brazil, Canada, and Sweden. Some of these operations move more than 100 million tons of material every year. Most people never think about this, but the steel in a single demolition excavator may have traveled over 20,000 kilometers before reaching the assembly line. The highest quality structural steel often starts with iron ore containing more than 62% iron content. After blasting and excavation, the ore travels by rail to ports and then across oceans aboard bulk carriers stretching over 300 meters long. Imagine standing on the deck of one of these vessels. Below your feet sits enough raw material to build hundreds of heavy machines. But steel alone isn't enough. The hydraulic cylinders that power these machines require chromium, nickel, and molybdenum. Chromium often comes from South Africa and Kazakhstan. Nickel arrives from Indonesia and Canada. These metals help create alloys capable of surviving immense pressure, abrasion, and years of punishing work. Then comes copper. A modern demolition excavator can contain hundreds of kilograms of copper wiring hidden throughout its electrical systems. Much of this copper originates from giant mines in Chile and Peru. Without it, the sensors, cameras, control units, and safety systems simply wouldn't function. What happens next transforms rough rock into engineering-grade steel. Inside blast furnaces reaching temperatures above 1,500 degrees Celsius, or 2,732 degrees Fahrenheit, iron ore combines with coke and limestone. The roar sounds like a jet engine. The heat radiates through protective clothing. Rivers of molten metal glow brighter than the sunlit sky outside. And this is where it gets truly extraordinary. The steel used in high-reach demolition excavators often undergoes specialized refining to achieve exceptional strength-to-weight ratios. Engineers constantly fight a difficult battle. Make the boom too heavy and the machine loses reach. Make it too light and it risks catastrophic failure under extreme loads. The environmental cost of this journey remains enormous. Mining operations consume vast amounts of energy. Steel production accounts for a significant share of global industrial carbon emissions. Manufacturers now invest heavily in recycled steel, electric arc furnaces, and cleaner energy sources. The race to build stronger machines increasingly depends on building cleaner supply chains. By the time these raw materials finally arrive at the factory, they have crossed continents, survived crushing pressures, and endured blistering temperatures. But the real challenge is only beginning. Because transforming thousands of individual parts into a machine capable of dismantling skyscrapers requires manufacturing techniques so precise that even experienced engineers stop to admire them. And that's where our journey goes next. The moment the steel arrives at the factory, an entirely new transformation begins. Imagine standing inside a manufacturing hall longer than several football fields placed end to end. Overhead cranes glide silently above you carrying steel plates that weigh more than a fully loaded city bus. What happens next surprised even experienced engineers when they first witnessed it. The first step is cutting. Giant steel plates, often between 30 and 120 millimeters thick, move onto CNC plasma cutting tables. Superheated plasma reaches temperatures above 20,000 degrees Celsius, nearly 4 times hotter than the surface of the sun. The cutting head moves with millimeter precision while showers of sparks explode across the factory floor. The smell of hot metal fills the air as computer-controlled systems carve out hundreds of structural components. Next comes machining. Massive components enter CNC milling centers where cutting tools spin between 2,000 and 6,000 revolutions per minute. Precision surfaces are machined to tolerances often tighter than half a millimeter. Every mounting point, pivot location, and hydraulic connection must align perfectly. A mistake too small for the human eye could create enormous stresses once the machine begins working. Now the skeleton begins to take shape. Workers position giant boom sections inside assembly fixtures weighing dozens of tons. Robotic welding systems and highly skilled welders work together, depositing kilometers of weld material into every structure. Arc temperatures exceed 6,000 degrees Celsius while brilliant flashes illuminate the factory like artificial lightning. The crackling sound echoes across the building. But here's what nobody tells you. Welding creates enormous internal stresses inside the steel. To prevent future cracking, some critical components undergo stress relief heat treatment. Giant furnace chambers heat the structures to roughly 600 degrees Celsius, or 1,112 degrees Fahrenheit, for several hours before controlled cooling begins. The process looks simple, but it dramatically improves long-term durability. While the structural components cool, another team builds the hydraulic system. Demolition excavators depend on hydraulic pressures that can exceed 350 bar, or more than 5,000 psi. Precision-machined cylinders, pumps, valves, and hoses arrive from specialized suppliers around the world. Think about this. A single hydraulic cylinder may generate enough force to lift dozens of family cars at the same time. Then comes the heart of the machine. Massive diesel engines producing anywhere from 300 to more than 800 horsepower arrive at dedicated assembly stations. Fuel systems, cooling circuits, exhaust treatment equipment, and electronic control modules are installed with extraordinary care. Every connection must survive years of vibration, dust, heat, and shock. What happens next transforms separate assemblies into a demolition giant. The undercarriage, counterweight, engine module, hydraulic system, and upper structure come together in carefully choreographed stages. Overhead cranes capable of lifting hundreds of tons move components into place. Every movement happens slowly because a single mistake could damage parts worth hundreds of thousands of dollars. The high-reach boom installation is one of the most spectacular moments in the factory. Some boom sections stretch dozens of meters and require multiple lifting points for safe handling. Engineers monitor alignment continuously as technicians secure giant steel pins and hydraulic connections. Watching the arm rise for the first time feels like seeing a mechanical dinosaur come to life. Once assembly finishes, technicians fill the machine with hydraulic fluid, engine oil, coolant, and fuel. Computer systems perform hundreds of automated diagnostic checks in seconds. Sensors verify pressure levels, fluid flow rates, electronic communication networks, and safety systems. A modern demolition excavator contains far more computing power than most people realize. Then comes the first startup. The engine roars to life. Hydraulic pumps begin circulating fluid through kilometers of internal pathways. The entire machine vibrates with controlled energy as operators slowly move each function through its full range. You can hear pumps humming, steel structures flexing, and hydraulic cylinders extending with immense force. Most people think the machine is finished at this point. In reality, manufacturing has only completed half its mission. Before this excavator can touch a real building, it must survive some of the toughest quality and durability tests in the heavy equipment industry. And some of those tests push these machines closer to their limits than most owners will ever dare. Before a demolition excavator earns the right to enter the real world, engineers subject it to a level of scrutiny that borders on obsession. Imagine spending years designing a machine worth more than $1 million, only to discover a hidden defect after it reaches a demolition site. That single failure could endanger workers, delay major projects, and cost millions. This is why every critical component faces an extraordinary series of inspections long before it leaves the factory. The first line of defense is laser scanning technology. Advanced scanners project thousands of laser points across every surface and create precise digital models within minutes. Computers compare the finished parts against original engineering designs and search for deviations as small as a few tenths of a millimeter. Most people never think about this, but even tiny dimensional errors can multiply into serious problems once the machine operates at full reach. Next comes ultrasonic inspection. Technicians move specialized probes across welded joints while high-frequency sound waves travel deep inside the steel. Hidden cracks, trapped gas pockets, or internal flaws reveal themselves on digital displays. The process feels almost like giving the machine an ultrasound examination. What happens next surprised even experienced engineers when these systems began detecting imperfections invisible to the human eye. Artificial intelligence now plays a growing role in quality control. High-resolution cameras capture thousands of images every hour while AI vision systems analyze weld beads, surface finishes, paint quality, and component alignment. Some systems identify defects with consistency levels exceeding 99%. The machines never get tired, never lose concentration, and never miss a scheduled inspection. But here's where things become fascinating. Despite all this automation, human expertise still matters enormously. Veteran inspectors often notice subtle visual clues that algorithms struggle to interpret. A slight discoloration, an unusual weld pattern, or a tiny surface variation can trigger further investigation. Sometimes decades of experience outperform the most advanced software in the building. Once inspections are complete, the machine enters structural stress testing. Engineers attach sensors throughout the boom, stick, chassis, and hydraulic system. Then enormous loads simulate years of real-world operation within a compressed testing schedule. Every movement generates streams of data showing how steel structures bend, flex, and recover under extreme forces. Think about this. Some fatigue tests cycle hydraulic systems hundreds of thousands of times. Cylinders extend and retract repeatedly while engineers monitor wear rates, pressure stability, and structural performance. The rhythmic movement continues day and night for weeks. What looks repetitive actually reveals how the machine may behave after years of demolition work. Hydraulic systems receive some of the toughest examinations of all. Engineers pressurize circuits beyond normal operating levels, sometimes approaching 420 bar during controlled test procedures. Sensors monitor for leaks, pressure drops, temperature spikes, and microscopic seal failures. The slightest weakness reveals itself under these extreme conditions. Then comes the stability test, one of the most dramatic moments in the entire process. The boom stretches outward carrying heavy test loads while engineers carefully evaluate balance and structural behavior. Watching a machine weighing hundreds of tons extend its arm high into the air feels almost impossible. Yet every movement follows calculations refined through years of engineering. International certifications add another layer of accountability. Manufacturers must satisfy demanding standards covering structural integrity, safety systems, emissions, operator protection, and manufacturing quality. Every approved machine carries evidence that it survived rigorous examination. Behind that certification plate lies an enormous amount of engineering discipline. Even after passing factory tests, many machines move to proving grounds that resemble industrial obstacle courses. They travel over rough terrain, climb steep grades, rotate continuously, and operate attachments under realistic conditions. Dust fills the air. Engines roar for hours. Every system faces one final challenge before delivery. And this is where it gets truly extraordinary. After surviving thousands of inspections, measurements, simulations, and stress cycles, the machine finally stands ready to reshape skylines around the world. But the story of demolition excavators extends far beyond the factory gates. The global industry behind these giants spans continents, employs hundreds of thousands of people, and generates billions of dollars every year. And some of the numbers behind that industry are almost impossible to believe. By the time a demolition excavator arrives at a job site, it represents the work of miners, steel workers, engineers, software developers, machinists, welders, inspectors, operators, and logistics teams spread across multiple continents. Most people see only the finished machine. What they don't see is the vast global industry working behind the scenes. And the scale of that industry is far larger than most people imagine. Today, the global excavator industry produces hundreds of thousands of machines every year across all categories, from compact units to giant mining and demolition models. The worldwide market generates tens of billions of dollars annually and continues expanding as cities modernize and aging infrastructure reaches the end of its life cycle. Every new skyscraper eventually creates demand for advanced demolition equipment decades later. In a strange way, construction and demolition have always grown together. The world's leading producers include China, Japan, South Korea, Germany, and the United States. Together, these countries account for a large share of global heavy equipment manufacturing. Some factories produce thousands of excavators each year, while specialized demolition models are built in much smaller numbers. That rarity makes the largest high-reach machines some of the most exclusive construction equipment on Earth. Think about this. The largest demolition excavators can weigh more than 200 tons and reach heights approaching 70 meters. That's roughly the height of a 20-story building. Standing beside one feels less like looking at a construction machine and more like standing next to a mechanical creature from another era. Did you know that modern demolition attachments can generate crushing forces measured in hundreds of tons? Hydraulic shears slice through structural steel that once supported entire office towers. Concrete crushers pulverize reinforced structures into recyclable material. What once required crews of workers with specialized tools can now be completed by a single machine operator. Here's another surprising fact. More than half a century ago, demolition often relied on wrecking balls swinging from cranes. The process looked dramatic, but it lacked precision. Modern demolition excavators can selectively remove individual sections of a structure while leaving nearby buildings undisturbed. Over the last 50 years, demolition has transformed from brute force into an engineering science. And this is where the future becomes fascinating. Engineers are developing hybrid and electric excavators that reduce fuel consumption and emissions. Advanced telematics already allow fleet managers to monitor machine performance from thousands of kilometers away. Some experimental systems even assist operators with automated movement control and intelligent safety monitoring. Did you know that some modern excavators generate millions of data points during normal operation? Sensors track temperatures, pressures, fuel consumption, hydraulic performance, boom positions, and structural loads. The machine continuously tells engineers how it's feeling. Most people never think about this, but today's demolition excavators are as much computers as they are mechanical machines. The workforce supporting this industry numbers in the hundreds of thousands worldwide. Every machine represents countless hours of human expertise. Welders shape steel structures, programmers write control software, operators master precision movements, and engineers solve problems most people never encounter. Behind every giant machine stands an even larger network of human skill. Over the next decade, experts expect demolition equipment to become smarter, cleaner, safer, and more connected than ever before. Artificial intelligence will improve efficiency. New materials will reduce weight while increasing strength. Alternative power systems will reduce emissions. Yet one thing will remain unchanged. Cities will continue evolving, and these machines will continue helping reshape the world around us. From ancient tools and wrecking balls to intelligent machines capable of dismantling skyscrapers floor by floor, the journey of demolition technology tells a remarkable story of human innovation. But after traveling from mines and steel mills through factories and testing grounds, one final question remains. Will you ever look at a demolition excavator the same way again? Over the last few minutes, you've followed an incredible journey. We started deep beneath the Earth's surface where iron ore waited inside vast mines. We crossed oceans with raw materials, stood beside blast furnaces hotter than most people can imagine, and watched engineers transform steel into machines powerful enough to dismantle entire skyscrapers. Every step revealed a hidden world that exists behind every demolition project. Think about this. When a demolition excavator reaches toward the top floor of a building, you're not just looking at steel, hydraulics, and electronics. You're looking at the combined knowledge of generations of engineers, operators, welders, machinists, and inventors. Thousands of decisions, calculations, inspections, and improvements come together in a single machine. Most people never think about that hidden story. But here's what nobody tells you. Demolition isn't really about destroying the past. It's about making room for the future. Every structure removed creates space for something new. Every carefully planned demolition project becomes the first step in the next chapter of a city's story. And these extraordinary machines stand at the center of that transformation. And this is where it gets truly extraordinary. The same machine that can crush reinforced concrete with immense force can also remove structural elements with astonishing precision. Power and control rarely coexist at this scale. Yet every day around the world, skilled operators use these giants to perform tasks that would have seemed impossible just a few decades ago. The next time you see a demolition excavator reaching into the skyline, listen closely. Behind the sound of engines, hydraulics, and falling concrete lies a story of mining, metallurgy, manufacturing, testing, technology, and human ingenuity. What appears to be a single machine is actually the result of one of the most complex industrial journeys on Earth. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.